It's pretty wild when you think about it. How can these massive billion-parameter AI models, the kind that are supposed to need huge data centers, actually run right on your laptop or even your phone? Well, there's a secret sauce, and it's a revolutionary C library called GGML. Today, we're going to get our hands dirty. We're diving deep into the code, the core concepts of GGML, and its sidekick, the GGUF file format, to see exactly how this magic happens.
And really, it all kicks off with this quote from its creator, Georgy Gerganov. This isn't some project cooked up in a giant corporate lab. Nope. This is all about that hacking spirit. It's built by a passionate open-source community, and the whole idea is to keep things simple and super efficient. It's about giving developers like you the power to build amazing things right on the devices we use every day.
All right, so here's the plan for today. We'll start with the GGML revolution, what it is and why it's such a big deal. Then we're going under the hood to look at the core concepts. After that, we'll jump into a C code walkthrough to see it in action, unpack the GGUF file format, and wrap up by looking at the incredible future of AI at the edge.
Okay, let's kick things off. So, what is the GGML revolution all about? At its core, GGML is a tensor library written in plain old C. But here's what makes it so revolutionary. It has this laser focus on one thing, running massive transformer models efficiently on the hardware you already own. We're talking about your standard CPU, the Apple Silicon in your MacBook. No fancy, expensive hardware required.
So, why are so many developers flocking to GGML? Well, it's basically the opposite of all those bloated, complicated frameworks. It's all about minimalism. The core library, it's tiny, totally self-contained. You don't need some crazy build system to get it running. The compiled binary is less than a megabyte. It's also super portable, running on pretty much everything. x86, ARM, Apple Silicon, you name it. And maybe most importantly, it's got amazing support for quantization, which is the magic trick for shrinking these giant models down to a size that actually fits on your machine. All right, time to pop the hood and get a little technical. If you really want to understand where GGML gets its speed and efficiency, you've got to understand its building blocks. This is where it's totally different from something like PyTorch. Instead of a black box, GGML hands you the keys and lets you see exactly what's going on.
First up, we have the GGML context. The best way to think about this is like your digital workbench or a memory sandbox. It's a block of memory that you allocate right at the start. Everything you do, all your tensors, your entire computation, it all happens inside this context. You set the boundaries, and GGML plays within them. Super efficient.
Okay, next is the GGML C-graph, and this is a really key idea to grasp. When you tell GGML to do something, say multiply two matrices, it doesn't just do it right away. Instead, it adds that operation as a little node on a graph. The graph becomes the complete blueprint, the step-by-step recipe for everything you want to compute. Nothing actually happens until you say, okay, blueprint is ready, go.
So if the graph is the blueprint, who's the construction crew? Well, that's the GGML backend. The backend is the thing that actually executes the plan on your hardware. It's the bridge between that abstract blueprint and the physical silicon. And this is the secret to GGML's portability. You can swap in a CPU backend, a CUDA backend for your NVIDIA card, or a Metal backend for Apple devices. Same blueprint, different crew. And to make things even more efficient, we have GGML Galilog. Think of this as a super smart resource manager. Before a single calculation is done, it looks at your entire blueprint, the whole graph, and figures out exactly how much memory it's going to need for every single step, including all those temporary results. This means it can allocate memory with almost zero waste, and even reuse memory spots the second they're no longer needed. It's incredibly clever.
So when you put it all together, you get this really deliberate five-step process. First, you set up your workspace, the context. Then you create your data, your tensors. After that, you build the blueprint, the graph. Only then do you tell it to execute the graph. And finally, you grab your results. See? Nothing is hidden. GGML makes you do each step on purpose, and that explicit control is exactly where its power and efficiency come from. Okay, enough theory. Let's see what this actually looks like in practice. We're going to dive into some real low-level C code. We'll just do a simple matrix multiplication, but you'll see how every single one of those concepts we just talked about fits together perfectly.
And this right here just says it all, doesn't it? Look at the difference. In PyTorch, it's one simple line of code. It's easy for sure, but there's a ton of magic happening that you can't see. Then look at GGML. You are explicitly in charge of everything, allocating memory, creating the data, building the graph, running it, getting the result, and even cleaning up after yourself. It's more work, absolutely, but that's the trade-off. You get complete control and, with it, incredible performance.
Okay, let's break down the code. Step 1 and 2. First, you can see we set up our GGML context, basically telling it how much memory to set aside for our little operation. Then, we create our two tensors, A and B, defining their dimensions. And notice that memcopy call. We're not just defining them, we are literally copying our raw matrix data into the memory that GGML is now managing for us.
All right, now for the cool part, building the graph. We create a new graph called GF, and then look at this line, GGML multmat. Now this is crucial. This line does not actually perform the multiplication. Not yet. All it does is add a multiply matrix node to our blueprint, our graph. It just makes a note that this is what we want to do. Finally, GGML build forward expand takes that result we want and builds out the full sequence of operations needed to get there.
And this is what you get. If you were to print out the graph structure, you see something exactly like this. It's a perfect text representation of the blueprint we just designed. You can see our one operation, mulmat, and the two inputs, or leafs, that feed into it. Again, no math has been done yet, but the plan is officially locked and loaded.
Okay, so we've got the computation engine down. But what about the data? I mean, how do we load the actual model with its billions of weights? Well, that's where the GGUF file format comes into play. It's the modern standard for packaging up these models for use with GGML, designed from the ground up to be super robust and easy to use.
And GGUF was built with some really smart design goals. First, everything is in a single file. No more chasing down a bunch of different assets. It's also extensible, meaning they can add new features to the format without breaking older models. But the real game changer is mmap compatibility. This is huge. It means your operating system can load the model without actually copying all the data into RAM. It's like creating a direct portal to the file on your disk. That's why a 7 billion parameter model can feel like it loads instantly. It's not copying gigabytes of data, it's just mapping it.
The structure of the file itself is actually pretty simple. It starts with a magic number, just a little signature that says, hey, I'm a GGUF file. After that, you've got all the metadata, stored as key value pairs. This is where you'll find everything you need to know about the model. Its architecture, the number of layers, its vocabulary, all the important stuff. And then finally comes the main event, the raw tensor data, which is where all the model's weights actually live.
Now, that tensor data we just mentioned is often quantized. And honestly, this is the real secret sauce behind running huge models on your laptop. So what is quantization? It's basically the process of reducing the numerical precision of the model's weights. The best analogy is a JPEG image. You take a massive, high-resolution photo and compress it. You lose a tiny, often unnoticeable amount of detail, but the file size plummets. It's the same idea here. By taking a 32-bit number and squishing it down to a 4-bit one, you can make the model 8 times smaller. That's how a 30-gigabyte model suddenly fits in your RAM.
So we have this incredibly efficient engine and a smart file format. The big question is, what has the community actually built with these tools? Well, the impact has been nothing short of massive, sparking an entire ecosystem of projects dedicated to AI at the edge. Just look at this list. I mean, the proof is right here. Llama.cpp completely changed the game, letting people run powerful LLMs on their MacBooks. Whisper.cpp did the exact same thing for super fast audio transcription. And then you have these amazing applications like Llama, Jan, LM Studio. All of them use GGML under the hood to make running local models a ridiculously simple one-click experience for everyone. This isn't just some academic project. It's the engine powering a real revolution.
And that, right there, is the most important thing to understand. The combination of simplicity and raw performance in GGML has created this incredible flywheel of innovation. It's a tool that just begs you to tinker with it, to hack on it. Because it's so straightforward, developers can try out new, wild ideas way faster than they could with some giant, complex framework. It just lowers the barrier to experimentation.
Which really brings us full circle, right back to that hacking spirit we talked about at the beginning. The tools are here, they're simple, they're efficient, and they're open for everyone. You now have the power to run these incredibly sophisticated AI models right on your own machine, privately and efficiently. So, the only question left is, what are you going to build?